Well, today I want to discuss about the oxidation numbers. What is oxidation number? Now, oxidation number may be defined as the apparent charge of an element in a compound or in an ion. Now, it's important to mention here that so far we know that atoms are electrically neutral. This is because the number of electrons and protons are equal. That means because the electrons are negatively charged and protons are positively charged, when they have the same number, what happens is that the negative charges are neutralized by the positive charges. However, when these atoms are involved in a reaction, because of either gaining or losing electrons in a reaction, then what happens is that their neutrality now
changes, and we may actually see them either increasing in charge or reducing in charge. Now, when they lose electrons, of course, when they lose electrons, what happens is the charge increases, therefore the oxidation number increases. But when they gain electrons, then what happens here is that their charge reduces. In other words, their charge will be negative, and therefore the oxidation number will reduce. So let's have a look at maybe some of the rules that we are going to use when we are assigning oxidation numbers. Now, one of them, elements will have an oxidation number of 0. We'll have an oxidation number of 0. For instance, talk about something like oxygen, talk about hydrogen, talk about not just non-metals, just talk about anything, talk about sodium, talk about magnesium, and so on and so forth. Now, these ones here will have an oxidation number of 0. Why? Because they are electrically neutral. Remember, these are atoms. These are two atoms combining. These are atoms. These are atoms. These are atoms. Therefore, they are electrically neutral, and therefore, they are going to have an oxidation number of 0. I believe that we already know this. Then the oxidation number of ions is equal to their charges. Talk of magnesium ions. This is the charge. Look at the charge of magnesium ions is actually 2 positive. Therefore, the oxidation number equals that one there, equals 2 here, and therefore it is actually plus 2. This one again is something that we've done before. Maybe in our form 2 you were able to note this. Now then, something else here, in compounds, look at that, in compounds, always hydrogen will have an oxidation number of positive 1. But there is some exemption where we have metal hydrides, where it is a negative 1. Of course, this one tells you something here. If I'm saying that they have an oxidation number of positive 1, that means in most of the circumstances here, or in most of the cases, when hydrogen is combining with other substances, it is going to lose an electron. And that's why in compounds, in most of the compounds, it will have an oxidation number of positive 1. However, in metal hydrates, that means where we have a compound of a metal and hydrogen, you can, for example, think about something like sodium hydride, where something like sodium here is reacting with hydrogen. In this particular case here, the fact that this sodium here has a higher tendency to lose electrons, what will happen here? It is going to lose electron, and hydrogen will acquire that electron. And that means here, a hydrogen, in this particular case here, will have an oxidation number of -1. That's what we're talking about. So every time you see the compounds, in the compounds there, any compound, hydrogen will have one, except such a scenario. Now with these others, of course, the other compounds like H2O, the oxidation number of hydrogen will be equals to +1, and many others, of course, many others you can think of. Now for oxygen, oxygen will have an oxidation number of -2, an oxidation number of -2. This again tells you here that when oxygen is being involved in most of these reactions, you realize that oxygen here will be gaining 2 electrons. That is what we actually are talking about. But also we have some exemptions. We also have some exemptions. This is where we can have things like peroxides. Now, for example, peroxides. Like for example, if I talk about something like sodium peroxide here, this is sodium peroxide. This is sodium peroxide here. Now, in this particular case here, oxygen here, the oxygen will have an oxidation number of -1. Therefore, during the formation of sodium peroxide here, each of these oxygen here will gain 1 electron. That is what we are talking about. Now again, if you think about something like the oxygen fluorides, look at that. Oxygen fluorides here, this one again will be different. This one here will be different. Oxygen fluoride, we can have it like that there. Oxygen fluoride. Now in this particular case here, now this oxygen here will actually have an oxidation number of +2. An oxidation number of +2 here. There's another scenario. So in this particular case here, instead of oxygen here gaining electrons, it is actually going to lose electrons. It is going to lose electrons. That is during the formation of oxygen fluoride. That's what we're talking about. Now, rule number 5 here, in compounds, the sum of oxidation numbers of constituent atoms here is 0. It is actually 0. This is what I'm talking about. Now, all the compounds that you can ever think of here, they actually have an oxidation number of, they are neutral. They are actually neutral. I want you to think, for instance here, if I think about any compound here, like for example, sulfur 4 oxide, this is a compound. This is actually a compound. Now, if you're going to take the oxidation number of sulfur, and then you add with the oxidation number of oxygen, and there are 2 of them here, it should give you a 0. That's what I'm talking about. Now, assuming that sulfur here has an oxidation number of X. It has an oxidation number of X. Oxygen, we've just mentioned here that always is going to have an oxidation number of -2. An oxidation number of -2. Now, therefore, what we're trying to say here is that if you are going to add these oxidation numbers of S, which happens to be X, oxygen, which happens to be -2 there, you multiply by 2. Now, if you sum all this, it should give you a 0. It should actually be able to give you a 0. Now, working on this one here, this will be X, -4 will be equal to a 0, and X, therefore, in this particular case here, should be equal to +4. It should be equal to +4. That's what we are actually talking about. Now, these rules, as you can see, can actually be able to help us to find the oxidation numbers of elements which may have more than one oxidation number. For example, sulfur, as you've just seen. That's what we're talking about. Now, well, having said this again, maybe we can also talk about one other rule here that maybe we ought to have here, and this is rule number 6 here. rule number 6, that the sum of oxidation numbers. Now, if we talk about an ion with more than one element, for example, think about something like a sulfate. I want you to think about a sulfate here. Look at that. Now, this sulfate here, you can see it has a charge of 2 minus. Now, with this rule here, if I'm working for the oxidation number of sulfur, which is actually this value for sulfur, it varies, and therefore, maybe if I want to check the oxidation number of sulfur, assuming that the oxidation number of sulfur is X, and we know that the oxidation number of oxygen here is actually -2, therefore I can have, because there's a 4 oxygen atoms, I'm going to 4, I multiply by -2 here, the sum of this should give me a -2. It should be able to give me a -2. Now, that means that this is X minus 8 is equals to -2, and X taking -8 on the other side, of course, you're going to have +6. And that will be the oxidation number of sulfur in the sulfate. In other words, during the formation of a sulfate ion, sulfur here loses the 6 electrons in the outermost energy level. It is going to lose the 6 electrons in the outermost energy level. So, and basically that is what we are talking about as far as oxidation numbers are concerned. One of the benefits of this, or one of the applications of this here, is to be able to monitor. It is actually to be able to monitor the movement of electrons during a reaction. The movement of electrons during a reaction. We'll be able to apply this, especially maybe when we're discussing about the redox reactions. In the redox reactions, we'll be able to discuss actually how we can be able to monitor. We can actually be able to monitor the movement of electrons by determining the oxidation numbers, and of course, we'll be able to tell what exactly is happening. Now, let us, having looked at the rules that we use in assigning oxidation numbers, I want us to get further and maybe try and work out the oxidation numbers of elements in compounds. Now, for instance, my first case here, I'm given a compound. The compound formula is M, capital M, small m, O2. That's manganese, and this is oxygen here. Now, how do I work out oxidation number of manganese in this particular compound? Now, as far as my rules are concerned, A, solution for A. Now, as far as my rules are concerned here, the sum of oxidation numbers of elements in a compound is actually 0. That means if I take the oxidation number of manganese here to be X, and then I'll have the oxidation number of oxygen here to be -2, and there are 2 oxygens. In other words, I'm going to multiply by 2 there, then I should be able to get a sum of 0. I'm going to get a sum of 0. Now, therefore, X here -4 is equals to 0, and taking -4 on the other side, it actually becomes a +4. That means that the oxidation number of manganese in this particular case here is 4, and therefore the name of this compound here is actually manganese 4 oxide. Manganese 4 oxide, that's what we're actually talking about. Now, let me go to B again. and we see what we are talking about. Before I get to this here, I must say here that in the formation of manganese 4 oxide, the atom of manganese here, the atom of manganese loses 4 electrons. An atom of manganese here loses 2 electrons, and actually the 2 oxygen atoms are able to get the 4 atoms. That means each of these oxygen here will be able to acquire 2 electrons. Now let me go to B and we think about the solution here. We look at the solution for this here. In this case here, I'm actually dealing with an ion. Now, as far as our rules are concerned here, the sum of oxidation numbers is equal to the charge of this ion. That means here, if I take the oxidation number of manganese here to be X, and the oxidation number of oxygen here, I know it is -2 here in all compounds except in peroxides, as we have seen here. I'm going to multiply by 4 because I have 4 oxygen here. I have 4 oxygen atoms there. And then this one should be equals to -1. Look at that. Should be equals to -1. Don't forget here, the -1 here should be the sum of the oxidation numbers of these elements here in an ion. Now, having said this, therefore, I'll have my X here, -8 is equals to -1. That means here that my X will be equals to -1 plus 8, taking -8 on the other side here, and obviously this one becomes +7. +7, that's what we're talking about. And that's therefore here, we can actually be able to call this ion here, we can call it manganate 7 ion. We can call it manganate 7 ion. Remember, it has some oxygen, that's why we have 8. Remember the 8 here, manganate 7 ion here, that we'll be adding ATE because it has some oxygen there. Therefore, manganate 7 ion, that's what we are actually talking about. Now, then the last one here, or maybe it could be almost the same as this one here, we are going to have our compound here actually made up of 2 chromiums and 7 oxygen there. Now again, we think about the solution for this. We look at the solution for this, assuming that the oxidation number of chromium here is X, and I have 2 chromiums here. That means I'll have 2X, and then I'm going to add my oxidation number of oxygen. We have said it is actually -2, so I multiply by 7. Now the sum of these oxidation numbers here should give me a -2. It should be able to give me a -2. Now that means here I'm going to have 2x here, then I'll have -14 giving me -2. Now of course, if I take 2x here, I'll have -14 on the other side here, so that it will be a plus now. So -2 plus 14 gives me a 12, and that x is equals to +6. It actually gives me +6. That means here, I'm going to call this ion here based on the oxidation numbers. Therefore I'll call it dichromate. Di because I have 2 chromium ions. Dichromate, remember it has oxygen, therefore 8 dichromate. I'm going to go to dichromate. And then I mentioned the oxidation number 6 iron. I'm going to call it dichromate 6 iron. That's what we are talking about. Therefore, I'm just trying to just apply the few rules that we have discussed about. Now, let me look at a scenario here. Let me look at a scenario where we can actually be able to use the oxidation numbers and maybe to try and explain what is really happening in a given reaction. In a given reaction, can we be able to tell in a reaction this particular substance is gaining electrons, this one is losing electrons based on the oxidation numbers? Let's have a look at that. Now, in my second example here, I'm going to have an equation, and in this particular equation here, we are required to identify substances that undergoes reduction or oxidation. Now, let's have a look at the key reactants in this particular reaction. We have manganate ions. Therefore, maybe I'm having a compound like potassium manganate 7 reacting with a solution of iron 2, for example, iron 2 sulfate, and they're supposed to be acidified. These manganate are supposed to be acidified, therefore it is actually acidified potassium manganate 7 reacting with a solution of iron, like iron 2 sulfate. Now, when these two react, you realize the manganate ions are normally purple. Manganate ions are normally purple, and you realize that the purple color will be colorless because the manganate ions, as you can see, they've been converted to manganese 2 ions, which are actually colorless. At the same time, the iron 2 positive here are normally pale green. The solution of iron 2 is pale green, and we are going to see it turning yellow due to the formation of iron 3 ions. That is what we observe. Now, my interest here is just to be able maybe to see what really happens in this particular reaction, because we are able to see the observation, but how about the explanation of exactly what happens? Now, let's have a look at maybe manganate. We've just mentioned about the manganate ions, and we've just said here that the oxidation number of manganate ions, of manganese in manganate ions, was actually positive 7. Of course, we did it by multiplying minus 2 times 4 plus x and equating to negative 1. It gives us, or it gave us, a positive 7. Now, the oxidation number of an ion like this one here, manganese 2 positive ions, we said it is equivalent to the charge of this particular ion, and therefore this one here is actually plus 2. It is actually plus 2. Now, what we are seeing here, and this is one of the applications of oxidation number, is actually to be able to tell a substance that has undergone oxidation or reduction. What we see here is that the oxidation number has decreased. Decreases. It has decreases from positive 7 to positive 2. Now, when the oxidation number decreases, we call that one reduction. And therefore, you'll be very correct to say that manganate ions have been reduced to manganese 2 ions. Have been reduced to manganese 2 ions in this particular reaction. Now, also, you could also be able to tell automatically here, every time, why does the oxidation number reduces from positive 7 to positive 1? Why does it reduce? Why does it reduce? This means here that 5 electrons are gained. 5 electrons are actually gained. Now, let's get to the iron, because this is the other major reaction that is happening there. We have the iron. Now, this one again is automatic. We have the charge of iron 2 positive is obviously it is 2 positive, the oxidation number is positive 2, therefore. That of iron, 3 positive here, you can see the charge is 3 positive, therefore the oxidation number here is plus 3. Now this one here, you can tell that the oxidation number increased. The oxidation number increases. Now the oxidation number, the increase in oxidation number here, we actually call it oxidation. And therefore it is correct to say, that the iron 2 positive, ions are oxidized to iron 3 positive. Now, how or why does the oxidation number increases? Why does the oxidation number increases, especially by a 1? By a 1, this means that 1 electron is lost. 1 electron is lost. Remember, we know that when electrons are lost, the oxidation number increases. The oxidation number actually increases. And therefore, basically, that is what we're talking about. We can actually be able, therefore, to say that the manganese ions here, our manganese ions, on the other side, you can say our manganese ions, this one here, undergoes reduction. It undergoes reduction, and we can be able to explain that. How do we explain this? The oxidation number of manganese is able to decrease, or is able to reduce from positive 7 to minus 1. Now, what about iron 3 ions? Iron 2 positive, sorry, here. This one undergoes oxidation. Undergoes oxidation. Now, if I was to explain here, we can actually be able to tell indeed that the oxidation number of iron here is actually increasing from positive 2 to positive 3. So basically that's what we are talking about. And you can actually be able to tell here in our balance, when you're balancing this equation, you can be able to tell here that because each of these manganese ions here is actually releasing 5 electrons. Each of these manganese ions is releasing 5 electrons here. 5 electrons here, sorry, 5 electrons are being gained, not releasing. Each of these is gaining actually 5 electrons. That means I require this ion here must lose 5 electrons. This ion must lose the 5 electrons. That's why when it comes to the balance here, I require 5 iron 2 ions. Each of these iron 2 ion here releasing 1 electron. So that when they are 5, they are going to release 5 electrons to the manganese ions. And from manganese ions are gaining the 5 electrons, and will be able to form, of course, the manganese ions. The manganese ions, of course. That's basically what we're talking about.